All right. Looks like we're live.
Okay, I see that we're live now. Right now it's your screen that's presenting. Oh, never mind, it's me now. All right, hello everyone. I'm Woody from the Piazza, one of the TAs that helps everybody or whatever. James is here with me, and we're going to be going over the final exam practice review problems. So I'm going to be doing all the odd problems with the exception of number 5, and then James will be doing all the even problems with the exception of number 6. We'll still do those 2 problems. We're just swapping them with each other. So I guess I'll get started. So let me go ahead and present my screen share, screen 1. And the first thing I was going to do before I actually started with number 1 was I just wanted to quickly review all the things that we kind of learned this semester. More specifically, the types of transforms and whatever else. So we have these 4 items that we kind of discussed this semester. We started off the semester with Fourier series. Fourier series is a mathematical device, let's call it, that allows you to analyze steady state frequency domain signals for both continuous and discrete time periodic signals. Then we learned the Fourier transform, which is the exact same thing, except for it's for aperiodic or non-periodic signals, both in continuous and discrete time. And again, this is for steady state frequency analysis. Now, what do we mean by steady state? Well, back in the differential equations class, we talked about solving differentials, and you had a forcing function, and sometimes you had a forcing function and sometimes you didn't. When you didn't have a forcing function, that was called a homogeneous state, or if I remember correctly, it was called a homogeneous state. But it meant, hey, when I have this system condition, this is the response, and it would usually decay, and it would happen for some period of time, and then you would find a steady state. But when you add a forcing function, you include some transient, something happens to the system, and then it will trail off into a steady state. And so our Fourier series and Fourier transforms do not include transients. They only give you the results for a steady state. But later in the semester, after the midterm, we started learning about Laplace transforms. And then after that, Z transforms. So Laplace transform is the exact same thing as a Fourier transform, except that it includes your transients. So you can get a full, complete description of your signals and systems. So I wrote here transients and frequency analysis. For the Laplace transform, it only applies to your continuous time signals. If you want to analyze your discrete time, you need to use the Z transform. And the Z transform is the exact same thing as the Laplace transform. It just handles the ability to include discrete time. So anyways, that's just a quick review of what these things are, all on one page. So with that, let's get into some actual problems. So I'm starting with number 1. So first we'll see what the question even asks. This is a Fourier transform question. Compute the continuous time Fourier transform for the following signals. And we have 3 different signals, X, Y, and Z. Now the first one is we have some signal, and we want to take the derivative of that. So that's fairly straightforward. So I'm going to go to my notes. And I have here my notes. I just rewrote the problem, the signal. And this problem is very straightforward. All we're going to be doing is using a basic transform pair and then applying the differentiation and time property. So if we go over to our key concept sheet, this is for the continuous time Fourier transform. So I'm going to scroll down to those tables. So the first table is always the properties of the Fourier transform, or the properties of X. And then the next table is your basic transform pairs, which is very useful because nobody wants to do this stuff by hand when you actually get out into the field, into the industry. So anyways, it looks like our signal was some exponential times a unit step. So we're just going to find an exponential times a unit step. And look at that. There it is. Exponential times a unit step. With the real part of A being right there, is greater than 0. And this is the transform pair. So that's straightforward. So I put that. I put that right here. So if you follow my notation, this is saying this is the Fourier transform of this quantity, and it becomes this. This was the differentiation in time property, though. The basic transform pair was this, 1 over 3 j omega. So the 3 comes from here, and the rest of it is just because you have a unit step and an exponential. Now that you have the basic transform pair, let's apply that differentiation in time property. So what is the differentiation in time property? So we're going to scroll up to the first table and find the differentiation in time property and see what it does to the signal. So when we have any signal x of t, and we want to take the derivative of that, what does it do to our transform? So we determined our transform was 1 over 3 plus j omega, but we just have to include this extra j omega, and this extra j omega handles this differentiation to the signal. And so that's all you do. It's very, very straightforward. So let's move on to the next one, part B. So part B is our y of t is a exponential times a unit step, but time shifted. You can see we have a time shift here. And luckily, our time shift is the same for both terms. Our next problem will have a different time shift, and we'll learn how to handle that. But this one is very straightforward too. So the first thing you're going to do is you're going to find a basic transform pair, which we already did in part 1, and that's this right here. So it's going to be the same exact thing, but now instead of applying the differentiation in time property, we're going to apply the time shifting property. So let's go back over to our sheet, to our table, and see what the time shifting property does to signals. So if differentiation added just this j omega, what does time shifting do? So time shifting is right here. And it looks like all we have to do is we get the exact same transform, but we just have to stick this in front of it. And e to the negative j omega t naught, where t naught is our time shift. So we have to determine our time shift and then just plug it into this new term. So what is our time shift? Our time shift is t minus 2. So we have a 2. So we're just going to plug in a 2 and stick that in front of our basic transform pair. So that's what I did here. All right, so part C, what do we do then? Part C, we have the exact same signal as in part B, but we have a different time shift to the exponential than we have to the unit step. And in other words, we have some signal or system that has a time shift to it, but we turn the system on at a different point in time. And that's a conceptual way of thinking about it. But what do we do mathematically? How do we actually handle the mechanics of solving that? So this one's a little bit more tricky, and so I have more notes. Let's see what I wrote here. So I rewrote the signal here. There are 2 ways to solve this. We can either use the definition of a transform and just do it by hand manually, or we can do a clever reorganization of terms. Now in this specific case, I'm not sure which one's a little easier. I think I'd probably just go with the definition, but once you get good at the clever reorganization of terms, I think this one might be faster. But if you're not very good at it, then the definition is probably faster. So anyways, I did the definition first. So I rewrote the definition here, and the definition just comes straight from our notes, our key concepts from the textbook. This is our definition of what a Fourier transform is. We're taking the we're taking the infinite integral, or I think they call that the indefinite integral of some signal times this complex exponential. So I did that. You just got to plug and chug away, essentially. So I rewrote my signal inside the integral, and then I added the definition term right there. And then I'm going to be using the exponent properties. When you have an exponent that has some summation like this, you can break them apart or add them. You can split them apart or put them together as needed, depending on your purposes. So it looks like the first step I did was I distributed this -3 to both these terms, this t and this minus pi over 4. So that's here. And then it was more apparent that I can split this exponent into multiple terms, which I've done here. So if you notice when I did that, and this is just the same exponent properties that we've been seeing all semester, this becomes, this is just a number. If I plug this into a calculator, there's no dependent variable. There's no t or any other weird variables. So this is just a number. Now, I don't know what this number is until I plug it into a calculator. It's probably 2.7 something. Well, it'd be more than that, I guess. But anyways, it doesn't matter. It's just a number. So you can put that in front of the integrand and not worry about it until the very end. So that's what I've done here. Now, the other step I did as I was plugging through this, which I did earlier, but I didn't mention it, was I handled my unit step. So it looks like I have a unit step right here. And we all know that that just modifies our terms of integration. Our definition has us going from negative infinity to infinity, but a unit step means that you don't even turn on this system or this signal until some point in time. And this is some point in time in the future. Or I guess that would be the past. But anyways, this just modifies the bottom integrand. So that's what I've done here. And now that I've done those two things, I've split this out and I've handled the unit step. The rest of it is just, you're just taking an integral of an exponential. And we know what that is. You just basically stick the term in front. You stick the term in this and you put it in front, which I've done here, which is technically really just this part, where this came from, from this here. And then I'm just going to evaluate my actual my integration at the two endpoints, 2 and infinity, and just plug and chug. So I have my infinity here and my 2 here. It turns out that this exponential evaluated at negative infinity becomes 0. So I have that here. And then I have a negative here. It looks like I have a double negative. So these double negatives will cancel each other. And then I get to a final result after getting through the mechanics of the integration of this. This is my final result. And I like to keep my terms split so that I can identify them. This was our basic transform pair that we saw in parts A and part B. This was just some weird number that came from that weird phase shift. This weird phase shift here. And then this came from the time shifting property, which we saw in part B. But that was one method. That was using the definition. So now the next method was the clever reorganization of terms. Let's get into that. What does that mean? Well, starting here, we start solving that clever reorganization of terms. So this is what we have. This is the problem that was presented to us. And if we're going to use the time shifting property outright, without any extra first steps, or without having to plug through the whole definition integral, we need to get this, what we have, into this form, into what we want. So we need to take this signal and turn it into something that looks like this. Because what we want is that we want this phase shift to match our time shift. Remember, our time shift is t minus 2. And we have a t minus pi over 4. So we need to get this t minus pi over 4 into t minus 2 somehow. So how do we do that? Well, that means that I'm going to have to multiply what I was given by something that will, somehow cancel out this minus 2 and make it so that we can legally put this minus 2 here. So the way we do that, well, the first thing I did was, I have some e to the a, but I distribute this -3 to this t and this -2, which I did here. And then what do? Well, I need to find some value that will cancel itself so that I can legally put this 2 in here. So I'm going to get rid of the +6. The +6 came from this -3 times -2 is +6. So get rid of this +6 and add a 3 pi over 4, a positive 3 pi over 4. What that allows me to do is I can get rid of this 3 pi over 4 and get rid of this 6. So let's see. That's what I did here. This is e to the a. I'm sorry, this is e to the a right here. So I determined a to be -6 plus 3 pi over 4. and that will perfectly cancel with what we are given in the problem to create what we want in the problem, so that we can use that time shift property. So if just to verify, you know that the exponent properties allow us to add these two terms together and put it over a single base. So what is minus 6 plus 6? That's 0. And minus 3t plus 3 pi over 4 becomes minus 3t plus 3 pi over 4. And that recovers the original problem that we were given. This right here. Hopefully that makes sense. And I just verbally said the sanity check. The sanity check was to actually plug and chug and see what happens, and then you return your original problem. So now that we've done that, we've created this e to the a. This is e to the a right here, and we reorganized our signal into a form that now matches our unit step. We can then use the time shifting property as we did in part B, and then you just add this e to the a here, which is just a number. It's just a constant. So doing that, this becomes our final result. And you can see that it matches our final result from when we did it by hand using the definition of a Fourier transform. So we have the same three terms, the 1 over 3 plus j omega, which is our basic transform pair. We have this e to the minus 2 j omega, which is our time shifting addition. And then we have just some weird number that came out. And that was because of this e to the a that we created so that we could use the time shifting property. So hopefully that makes sense. And that's it for number 1. So now we're going to go on to number 2. And James will be picking this one up from here. And then I'll see you guys in a little bit for number 3.
Okay. So I think I'm presenting. Well, now you're presenting. Now I'm presenting. Okay. For number 2, we are asked, we're given this system here, which an impulse response h1 of t convoluted with another impulse response of h2 of t. And eventually we're going to get to what is the overall system response of this. But first, we're given the input function as t, or the first impulse response as t times e to the minus 2t times the unit step function, and asked to calculate its Fourier transform. And we're also given h2 of t as sine of 0.3 pi t, and asked to do its Fourier transform as well. So that's the first 2 parts. So we're given that we know from table 4.1 and in section 4.3.6 of your book that the form t e to the negative 2t is just t e to the negative, or is differentiation in the frequency domain. So we know that our Fourier transform will be j times the derivative of the Fourier transform with respect to omega. So we're doing differentiation in the frequency domain, so we got to calculate from this form. We know that we have this property. So from table 4.2, it's just easier to use the table to do the Fourier transform. We see that e to the negative alpha t times the unit step function is 1 divided by alpha plus j omega. That's, I mean, you can put it in the integral and crunch out the transform, but it's just go. You'll see these e to the alpha t's quite a bit, and it goes to this form right here. So we know we have plugging that in up here. We have j times the derivative of 1 divided by 2 plus j omega. So we take the derivative of it. I do it the way Khan Academy taught me. I guess you could use the quotient rule, but it's annoying. So I just put it as -1, use the product in the chain rule. So taking the derivative, bring the -1 down to give us a negative j times the stuff inside, 2 omega, 2 plus j omega, and then increment or decrement the exponent, and becomes -1 becomes -2. Then you take the derivative of omega with respect, or derivative of 2 plus j omega with respect to omega. So that derivative is just j. So then we get this form here. So we plug all this together. We get negative j squared over 2 plus j omega squared. We know that j squared equals -1. So we have -1 over 2 plus j omega squared. And then you get the 1 plus 2 j omega. And then I put a note on here, or we could look one below on that chart I used that had the actual one that would be useful as well. And I didn't do that. But hey, our numbers lined up with the same as what it should be in a chart. So that means we took the derivative correctly. Anyway, for signal 2, we're given it's equal to sine 0.3 pi of t. So our Fourier transform, again, using the table 4.2, we see that sine omega t equals pi divided by j times the delta function of omega minus omega 0 minus the delta function of omega plus omega 0. Our omega 0 in this case is 0.3 pi. So we just plug that in, and there's our equation. Now, for part C, we're asked what's the overall frequency response, and we see these two feed into each other. So they, in the final review, it shows it, but this is convolution into the time domain, and so that would be multiplication in our frequency domain. So we just have to multiply our two signals together of h1 j omega and h2 j omega. Doing a little simplifications, we get this function here, or you could have it in this function. Either one should be all right. This is just the 1 plus 2 j omega squared distributed through the step functions, or the impulse functions. And then number 4 asks us to calculate the overall frequency response. So we have to do an inverse Fourier transform. So we have to get this into something you recognize. Getting down to here, sorry, we'd use a sampling process, the sampling property. We know that this is only going to be not 0 when omega equals 0.3 pi. So we can just basically take that 0.3 pi and put it into our omegas for this one. And then they become our coefficients, and the only thing we have dependent on omega is well, that was neat. So anyway, the only thing we have dependent on omega is their impulse functions. So taking the inverse Fourier transform of those, yeah. For C, your answer should probably be this. That's the most simplified version. That way, you'll get the most credit. All right, so going to inverse Fourier transform, we see that e to the j omega t is 2 pi times omega minus omega naught. So we have to get this into a 2 pi form. This pi comes over here. I didn't write it very well. What's the key? Yeah, and my answer is wrong because the pi came over, so this should be 1 and 1, not pi. So anyway, this 2 pi is up here, and I just put a 2 in the denominator to get the 2 in the numerator to get it into the form that we need to do the inverse Fourier transform. So we know our omega naught is 0.3 pi. So it becomes 1, make this a 1 over 2j times 2 plus j 0.3 pi squared times e to the j 0.3 pi t minus 1 over 2j times 2 to the minus 0.3 pi, or 0.3 pi, there should be a pi there, squared, times e to the negative 0.03 pi t. So any questions on that? I mean, it's a fairly straightforward. Convert it to the Fourier transform, combine it with multiplication, and then convert it back. This keeps us from having to do our convolution integrals, and because the convolution integral on these could be this one probably especially would be annoying. So any questions or anything? I'm going to turn it back over to Woodson for problem 3.
Okay, I'm back, and for number 2, I also did. I initially made a mistake on part D as well. I'm not sure if it was the same one that James made here, but I just wanted to point out that you got to be careful when you're looking at your transform pairs. You want them to be in the exact form that you need them to be. So if you look at my scribbles here, looking at the professor's notes, his product, he chose this transform pair, e to the j omega naught t turns into 2 pi delta of omega minus omega naught. And when I saw that originally, I thought, why use that when we could use this transform pair here? But I was wrong, and you have to be very careful and pay attention to that kind of stuff. And it was, if I remember correctly, there was some term that didn't match up correctly. So anyways, I just wanted to point that out. I can't quite find it right now in real time, but look over my notes on your own time. Hopefully it'll pop out and it'll make sense, but you got to be very careful, that kind of stuff. But let's go on down to problem 3. So problem 3 asks, it's another Fourier transform problem. The Fourier transform x of j omega of a continuous time signal x of t is shown below. What is x of t? So we're given the frequency domain image of it, or like a graphical representation of it, and it's basically just a pulse. It's a pulse train, and we know that our frequency domain stuff mirrors across the the y-axis. When I say y-axis, I mean, well, the x-axis is the omega axis, but the y-axis is I don't remember what we call it, but anyways, yeah. So your frequencies always mirror it, so that's why you have this symmetry across the y-axis. But anyways, so it asks us, what is x of t? So the first thing we need to do is let's turn this into a mathematical representation instead of just a picture. So here I redrew the picture, just a pulse, and then I turned it into some mathematical terms. I translated it into a mathematical term from a graphical representation. And basically, it's just it's a 1 when omega is less than pi over 2, the absolute value of omega, so that handles the symmetry in the negative side of the axis, and then a 0 everywhere else. So basically, we're just going to go to the transform table and look for that pair. So let me go over to this chapter 4 key concepts sheet and scroll on down to our basic transform pairs, and let's find it. And remember, we were given the transform pair, so we need to find the signal. So I'm going to be looking for these center column values until I find something that is shaped the same. And there it is. So x of j omega equals 1 when the absolute value of omega is less than some value, and it's 0 everywhere else. So if that's what I'm given in the problem, then that means that the original signal was some form of this. So all we have to do is figure out what W was. So what is W in this case? W was pi over 2. And that comes straight from the picture that we were given, pi over 2. So basically, I just plugged that in and put our basic transform here. And that's part A. So it's very, very straightforward. Just look for, the transform pair on the table, and then you're done. Now, part B asks for something a little bit more complex. So part B says, sketch the Fourier transform P of j omega of P of t if P of t equals cosine pi t over 2. So basically, it gives us a time domain signal, and we call it P of t, and it wants us to sketch the Fourier transform. So let's do that. So here I rewrote what we were given, and then here I need to convert that into the Fourier transform so that I can draw a picture of it, because I can't just do it directly. I need to transform it first. So again, we're just going to look for the transform pair for cosine pi t over 2, and that's a very straightforward one, a very common one. No extra manipulations required, and here it is. So cosine omega naught of t, where our omega naught happens to be pi over 2. So that means that our transform will be this long thing, and it looks a little intimidating, but it's not. It's just 2 delta pulses multiplied by a scaling factor of pi. So normally the delta pulses are a magnitude of 1, but we just multiplied it by pi. So now there'll be a magnitude of pi. Also, our delta functions will not show up at 0. At omega equals 0, it's gonna they're gonna be shifted to some value omega naught. So our value, our shift is pi over 2 because it's given to us pi over 2. And you know, I have the symmetry across the y-axis, like we always do with frequency domain signals, and then we scaled it by pi. And I just rewrote it here so that I put my scaling factor in front of both terms, so it's a little easier to visualize. And then I visualized it, and all these are is just a impulse, just an impulse function at 2 values, and they're both scaled to pi. So pi over 2 minus pi over 2, and that's it. So that's part B. Now part B, I think it gets even more complicated. So part C wants us to sketch the Fourier transform y of j omega if y of t equals the product of x of t and p of t. So we had to figure out x of t in part A, and then we were given p of t in part B. So we need to multiply them together and see what happens. So let me scroll. Well, I'm going to keep it so we can see the whole problem still. So I just rewrote what we need to do. I rewrote what we determined x of t to be in part A, right here. And then I rewrote p of t, which was given in part B. So let's multiply them together. So we have a sine and a cosine multiplied together all over pi over t. So let's take the Fourier transform of that. And we know that in the time domain, when you multiply 2 signals together, you're really just convoluting them. And so I wrote basically the definition here. Whenever you have multiplication in the time domain, it becomes a convolution in the frequency domain. But now that we've determined that, our p of j omega is just a bunch of delta functions, right? So we can use the sifting property to simplify that convolution. Otherwise, convolutions are, you know, they suck to work with. You know, they're tedious. So let's actually go through that. So here I rewrote what we're trying to find. And I didn't put it in terms of x of t explicitly. I didn't evaluate x of j omega. I'm just keeping it in this x of j omega form because I know that it doesn't matter what x of t is or x of j omega is, because the sifting property will just modify it so that it is shifted by some new value according to the delta functions. According to the delta functions that were given by p of j omega. So now that I've done that, and here I just canceled our pi terms. So our final result becomes this, not given in explicit terms of x of j omega. So whatever x of j omega is, we're just going to shift it by this amount. So and we're going to scale it. We're going to rescale it to half the amplitude it was originally. So let's scroll up to see what we were originally given in part A. This was our original signal, and it was given to us graphically. So we don't even need to worry about the mathematical representation of it. This is what it looks like. So we just need to take this and scale it by half. So this was a magnitude of 1, but now it's going to be a magnitude of half. And then we're going to shift it out by these 2 values, pi over 2 and minus pi over 2. So they were starting and ending at minus pi over 2 and pi over 2. So we're just going to go out another pi over 2. So what's pi over 2 plus pi over 2? That becomes pi. So we have the power, the amplitude, and we spread it out over a larger area. It's kind of interesting to note, if I took the area of this, I think it equals the area of this. We just spread it out. But anyways, that's problem 3 in a nutshell. So let me know if you have any questions. And if not, we're going to move on to number 4, and James is going to take it back up from here.
Yep. Funny thing, I forgot time shifting property on number 3, so I actually worked out the integral. It sucked, but it did come out with the same thing. So I just wanted to show this real quick. That you can work it out the integral and it will be correct. So anyway, number 4, we are asked. This is a discrete time Fourier transform question. Compute the discrete time Fourier transform of the following signals. So we're just given 3 signals and asked to compute the discrete time Fourier transform. So on number A, or letter A, we're given 1/3 of the negative n times u times a step function of negative n plus 2. The key uses time shift and makes the basically the 1/3 of the negative n, the n match these two, and then pulls out that coefficient. I get confused with that. Like, am I going backwards? Am I going forwards? This is time shift and time reversal. I just threw it into the summation to calculate the Fourier transform. I find that easier for me. I'm less likely to lose negatives. So we know to get our Fourier transform from a discrete time, this is the equation, the general form. Plugging this in, we get these two. So then we want to use this to address our limits. So we're given negative n plus 2. So we know this is active whenever this is 0 or more or greater than 0. So taking the argument, we find out that n has to be less than 2. So that changes our positive infinity to 2, which I represent here. And our negative infinity is still there. We have 1/3 to the e to the minus n times e to the jw n. This can be thought of as e to the jw to the n. So you can just throw the e to the jw in there with the minus n because both have minus n. So now we have this term in here, and the negative n is weird. So we just reverse our limits. Everywhere, all our values of n that were positive are now negative. So we just reverse them. So now our sum is going from negative 2 to infinity times e to the jw divided by 3 to the nth power. This looks a whole lot like a geometric series because it is, but we have a nice little equation that lets us find what a geometric series converges to if our n start at 0. So we have to shift this to get our n's to be 0, or to start the series at 0. So we can change this into n minus 2 and then 0. So every time, the way I think of this is like if I were to plug in 0, I get e to the jw to the negative 2. If I were to plug in 1, I get the next term in the series, and then so on and so forth. That's how I remember how to do that. So it's a little sanity check to make sure I've shifted the right direction. Using the property of exponents, we can just make this equal to e to the jw to the third to the minus 2 as just a number. We're no longer dependent on n in this term, and we have this term still factored in. So this one I just outright calculated, and then this one I use the geometric series, and combining them all together, we have this on the numerator 9 times e to the negative 2 jw, divided by 1 minus 1/3 e to the jw. And so that all worked out to the same answer as the key, which means it's cool. So hopefully I didn't confuse anybody. That's my process. I don't know you can realize that I need the step functions driving the time shift. So I need this to look like this. So you can pull out that function and then use the table as to get your transform. Or you can always, if you get confused by the table, you can always throw them into the general equation and crunch them out. So for 2 or B, we're given the step function becomes active at -2 and then turns off at -3. So if you were to graph this, you just have 4 pulses, 1, 2, or 5 pulses, starting at 2, ending at -2. Then we can do the realization that this is a piecewise function, and where the magnitude of n is less than 2. So we use table 5.2 and find this transform, and we know our n1 is equal to 2. So we just plug that in, and we get this nice neat little function. For z of n, or for c, the last one, we're given the same function, just shifted. So on this one, I actually did do that. So we have to basically we recognize that z of n is y of n minus 1. And I tested it out, plugged in the values to make sure it was true. So now that we have the function and it's time shifted, we can use table 5.1.533 that says x to the n minus n0 is equal to e to the jw minus n0 times x of e to the jw. So this is y e to the jw, which we calculated up here. I actually went and plugged it in again and recalculated it. But then we have a coefficient for our time shift. Because we're time shifted by 1, that just becomes x to the e to the negative jw. So we get our overall Fourier transform of that signal becomes z times e to the jw, or equals e to the negative jw times sine of 5w divided by 2 plus sine of, I guess it's omega, not w. I keep saying w, but omega divided by 2. And I'm going to keep going with problem 5. It's another discrete time Fourier transform. It's much like 1 and 2 were for 5 and 4 and 5. So we're given the signal of h1 of n is 1/2 to the n times the unit step function. Find the Fourier transform. H2 of n equals sine of 0.3 pi n times, and that's again our Fourier transform for that signal, which looks awful lot like what we did up here, except we're not differentiating. So anyway, for problem 5, just this one is a straight table table conversion. Or from the table, we know that 1/2 to the n times u of n is this. So I always think of 1/2 of the n like some value less than 1 to the n. It's almost like the e in the discrete time, because you get pretty close to the same transform. And maybe that might confuse you. I don't really know if that's even right thinking. So anyway, for part A, straight table transform. For part B, again, another straight table transform. For this one, we used time shifting, or time sifting. I think it's time sifting to get the to go from here to there. Basically, we know that omega minus 0.3 pi minus 2 pi L has to be 0 for this to be anything. So that allows us just to sift these out and get rid of our summation. For part C, we have part C asks for the overall frequency domain function, H1n, H2n. So that's convolution, which is multiplication in the frequency domain. So we just multiply them out and get this nice little. That's pretty much it for 5. See if my key. See if I can match it with the key. And yep, pi over j. So hopefully that, and I have start of 6 there, but I'm going to turn that back over to Woody for 6.
Okay, back to me. So I was looking at my notes on problem 5, and I had a cool little note here talking about aliasing. I wrote aliasing permutations. That's just how that's my nomenclature. But anyways, on this transform pair for sines, and this is true for cosines too, or any trigonometric transform, because they always become delta functions. On our transform pair for that, we have this weird L term. And let me go ahead and go over to the sheet. That way we're not looking at my ugly handwriting. Let's see, we need to go to chapter 5. Discrete Fourier transform. And I'm going to scroll down until I find these transform pairs for our trigonometric signals. And we have this L term. I don't know if this is any better than my handwriting if I zoomed in, but this is an L to negative infinity to positive infinity. We have a summation of some delta function that is shifted by some arbitrary amount, but we add this weird term here. What does that mean? A lot of people just skip over, and it's like, you know, it is a big deal, but it's not a big deal when we're solving problems necessarily, but it is a big deal conceptually. And what this is for is it's for aliasing. So we learned in what aliasing is, and I actually have some cool tabs over here showing us pictures of aliasing. So aliasing is when you could have a signal, and if you aren't sampling it properly, if you're not taking enough samples rather, and you're not meeting the Nyquist rate, you could say that your discrete sampled output, or you know what the computer is seeing, if this is a computer, you know, because computers are discrete time machines. There's an infinite number of signals that could line up to those exact points that is sampled. So this image that I have here, I have my samples are these black lines. Let me zoom in actually. Actually, I guess I can't zoom in. Let me go back. Oh boy. Okay, there we go. So these black lines are our samples. So it looks like every second we're taking a sample in this particular system. Now every time we take a sample, we just capture some value. That's it. So at 0 seconds, we have some value at negative, let's call this negative 0.25 or something. At 1 second, we have some positive 0.25 value, and so on and so forth. We're just capturing magnitudes at very discrete points in time. But this picture shows us that for each of those points in time that we've captured the magnitude of a signal, we have an infinite number of signals that can line up to that. On this picture right here, I only have 2 signals, but imagine you can have an infinite number of signals that line up to this. We have a very high frequency that happens to coincidentally line up perfectly, and we have a very low frequency signal that happens to coincidentally line up to the same points in discrete time. And that's aliasing. If we didn't, to be able to distinguish this long wavelength frequency from this short wavelength frequency, we need to increase our, we need to increase our sample rate to be able to capture more points. So if I just doubled the number of times we took samples from 1 second to every half second, we would be able to determine that these 2 signals are not the same thing. But we can't if we're undersampling like this. So that's what aliasing is. And let me get back to this here. Maybe it's better with my handwriting. If I have some signal sine of omega naught n, and I've undersampled it, then there are infinite numbers of delta functions that can be represented, that can represent the same signal. Because if we've undersampled it, you know, we don't really know. There's all these other ones out to infinity that could represent the same points that we're taking our magnitude measurements at in discrete time. Hopefully that makes sense, and that's what that L term is for. It's for all of the aliasing permutations out there to infinity that could line up to our samples. So hopefully that makes sense. And with that, now we're going to move on to number 6. So let's see what number 6 is even asking for. It's a sampling problem. And it's good that I kind of mentioned aliasing and sampling, because we're going to now work with another sampling problem. Number 5 was not a sampling problem. So this is the first time we see sampling on this review sheet. So the question is, consider a continuous time signal x of t, and x of t is sine of 2 pi t over pi t squared. So basically we have two sine functions squared. So the first thing it wants us to do is plot x of j omega. It wants us to take the transform of this and then plot it. So let's do that. So here I rewrote the problem, and I rewrote it more explicitly. So we have this square here. It looks like my scanner didn't quite capture my entire page, but that's a 2. That's a square. And really that just means that we have this times itself. You know, obviously everybody knows what squaring is. I don't want to. Anyways, so our transform pair, when we have two signals multiplied together, is really just the convolution of those two signals times some other scaling factor. The 1 over 2 pi is a scaling factor. So I do this graphically. We do this graphically because I'm not sure if the problem gave us this image, because normally the professor writes in red when he writes it himself. But anyways, it doesn't matter. We know. Why did I write this? Let's see. Let's go look at the transform table, the transform pair table, and see why I do this graphically. So we're going to find this in the transform table, and it probably makes sense. I'm almost willing to bet it does. So let me zoom back out. And we're going to look for that same type of signal.
Yeah, it's just that x of n is 1 when n is greater than, yeah, that one.
Yep. All right, so that's why I said do it graphically, because we know that when we're given a signal that looks like this, it becomes this pulse. And this is just a simple pulse, so that's why we can draw it graphically. We don't have to worry about any weird curves and sinusoids and things like that, because it's just a pulse in the time domain. So if we're squaring this, that just means that we have two of these pulses multiplied by each other. So that's why I wrote, or convoluted rather, not multiplied. So that's why I wrote do it graphically. So we're going to be scaling it by 1 over 2 pi because that was given in the transform pair. And I have this image convoluted with this image. And we've seen this before on homework problems. So hopefully you remember it. But when you convolute two square pulses with each other, it becomes a triangle, a triangular pulse. And you expand your starting points and ending points out by that same amount. And luckily these two are the same, so we just know that it becomes a 4 pi. If this happened to be a different square pulse, like a different shaped square pulse convoluted with this square pulse, then you would have to do it by hand and use your definition to solve it and stuff. Otherwise it's easy since these are the same. Now we have the scaling factor, and here's that scaling factor right there. We get this 4 pi here because 1 convoluted with 1 becomes basically it becomes our starting point traveled over the length of double these pulses. If you can imagine these this moving forward through this pulse, like you've seen the visualization on hopefully on the Wikipedia page or elsewhere, you're basically just multiplying by this value here, and that's where you get that from. But then you simplify this and it becomes 2.
Sorry, I just want to. It's the area of both those squares would be your peak area.
Yes. Thank you. That does kind of simplify it in my mind. Yeah, it's the area of these two pulses here. So that's where you got this image from, is just the convolution and the rescaling of these two square pulses. So that's part A in a nutshell. So now let's go to part B and see what it asks for. So part B says if the basically this is a sample rate. If the sample rate is 0.2 seconds, plot x of p of j omega. X of p means a pulse train, which is, a pulse train, how do I say this? A pulse train measuring x of j omega. What is the Fourier transform of x of p of t when x of p of t is defined in this way? And I said it with words, but x of p of t is basically just your signal sampled at a specific rate. And that's all this term right here means, is that we're taking a bunch of delta functions that are at different points in time, different points on the t-axis, and remember in the sampling property of delta functions, that just means we're returning the value of x of t at those points in time. So basically, in other words, that we're just taking we're just sampling this signal to recreate it or represent it in a discrete way, I guess, so that a computer could handle it, for example. So let's see, what do I do to solve that? Part B, I rewrote what it gave us, and I already explained this note here. It just means I'm sampling the signal, and we're calling this whole thing P of t. This whole thing is P of t. I just do that for convenience. So the first thing I want to do is take the if I'm calling this P of t, I want to take the Fourier transform of that. So that's what I did here. So this was what we were given in the problem. And then we're going to be taking the convolution of our x of t and our P of t to return our answer. The question was asking for what is the Fourier transform of x P of t. So I wrote that here, and this is just like we did previously, except that we have to handle this 1 over. We have a period. We're given a period, so we need to include that in our convolution. And this came from this right here. This was the definition of a pulse train. And then our 1 over 2 pi, came from the definition of convolution when you are multiplying in the time domain. And then basically from here, it's just plug and chug. Now I plugged in my value. So 1 over 0.2 becomes 5. And I plugged that in here. The 2 pi cancels with this 2 pi, so I didn't put a 1 here, but implicitly there's a 1 there. And then I just rewrote this term here, plugging in my omega of s. My omega of s is 10 pi, and that just came from the inverse of this, basically. I'm sorry, it came from this. It is the inverse of the time, but you have to remember the equation. I didn't write it on here, but the equation for 1 over t equals f, f being the frequency, but f the frequency is in the time domain, but we're working with angular frequency, which is a frequency domain term. So how do I convert f into omega? Well, you have to multiply by a 2 pi. So I didn't write that here explicitly. I probably should have, but everybody should be familiar with that already. So hopefully it's not confusing. But anyways, now that I've plugged and chugged this into a full expression, I can then plot it graphically. And this just says that I'm taking my x of j omega and I'm scaling it by this amount. And I'm doing that over and over and over again, because that's what this k is here, this infinite sum of k values. We're going to do this over and over and over again every 10 pi. So we figured out in part A what our x of t was, our x of j omega rather was. It's just some weird triangle. And if this result says that we're going to have a whole bunch of them spaced out every 10 pi, well, that's all I have to draw. So I have my original one, and I go out 10 pi. So this triangle was centered at 0, so plus 10 pi is over here. And then I center a new triangle. Minus 10 pi, I center another triangle. And then the only other thing you have to worry about is there a scaling factor that we have to worry about? And yes, there is. The original amplitude of our original x of j omega was 2, right? Right there. And we are scaling it by 5. So 2 times 5 equals 10. And so that's our new scaling factor. So that's part B. So now let's move on to part C. What does part C ask us? Part C says, for what values of t sub s would aliasing occur, and justify your answer? Well, I explained what aliasing is earlier. Aliasing just means that if you sample at a specific rate and and the frequency of the signal that you're sampling is larger, or higher rather, and you don't meet that Nyquist rate, then, well, if it doesn't meet the Nyquist rate, you're going to have aliasing. So let's see what I did for part C. Well, here's the definition of aliasing. I accidentally wrote Nyquist, but Nyquist rate means that you need to have your sample rate be larger than your twice the max frequency that you're working with. So the way I wrote it here, where if my sample rate is lower than that twice the max rate, then that is what aliasing is. That is the definition of aliasing. So here I wrote what Nyquist is again, just to be explicit and clear so that it's not confusing. And all we really did was just change the direction of this equality. So anyways, in our signal here, are the largest frequency that we find, and I'm not talking about this one, I'm talking about the original signal, which is up here. What is the largest frequency that we find here? Well, it's 4 pi, because this signal is 0 everywhere else. So the largest frequency that we find is 4 pi. So that's what I wrote here. And then finally, well, how many samples do we need to take for aliasing to occur? We need to have twice that max frequency. So 2 times 4 pi is 8 pi. And then I need to convert this into time, into this time domain. So this is an angular frequency. So here's where I wrote my definition. I should have done it earlier in the problem, but I explained it. But here we can see it visually. So if I want to convert an angular frequency into a time, this is the equation to do that. And sorry, I ran out of room, but f equals omega over 2 pi, because 2 pi times f equals omega, the angular frequency, and that will equal 1 over t. So that's how I can convert this into this. And this is how I would write it with the equality for Nyquist, but we're not worried about the Nyquist, we're worried about aliasing. That's what the problem asks us for. So make sure that your equality sign is in the direction for aliasing and not for the direction of Nyquist, if your problem wants you to worry about aliasing. So in other words, our T sub S must be, if aliasing is going to occur, our sample rate, our time for samples must be greater than 2 pi over 8 pi. And that simplifies to 1 over 4. And 1/4 is 0.25 seconds. So remember, we're talking about seconds. So this is our final answer. If our sample period, because time is a period, is larger or equal to 0.25 seconds, then aliasing will occur. So hopefully that makes sense. And that's number 6 in a nutshell. So now we're going to move on to number 7, and James will take it from here.
Well, I thought you were doing 7 too.
Oh, right, yeah, duh. So I'm doing all the odd problems. That's right, and I just took number 6 from him, and he did number 5 for me. So, anyways,
hard. Sorry.
All right, so I'm going to do number 7, and what is number 7? Number 7 is another sampling problem. So this time it asks us, the signal y of t equals x1 of t times x2 of t is sampled by a periodic impulse train. It is known that x1 of t is band limited to 500 pi and x2 of t is band limited to 1000 pi. What is the Nyquist rate of the signal? So let me go over to my notes and I'll explain what this is asking for. So here I rewrote what it gave us. We just are taking the product of two time domain signals, and we're not given what the signals are. All we're given is what the maximum frequencies are in those signals. And that's what band limited means. So, you know, when we're talking about frequency domain, if you have something, some pulse, or how do I describe it? Some signal over I could do this better visually. If we have some signal in the frequency domain and it, it goes over the omega axis, this is a band. We have a band. So we have a frequency at 1 pi, 2 pi, 3 pi, and we have an amplitude at each of these frequencies given by this function, right? So we're band limiting this, if this was our example here, or rather, if this was our example here, this signal is band limited to 4 pi. That's what band limiting means. Just means your maximum frequency. So in problem 7, we're told that our first signal is band limited to 500 pi and our second signal is band limited to 1000 pi. So rewriting that, just to show it mathematically, I guess, we're saying that our signal in the frequency domain is 0 everywhere except past 500 pi for the first signal and 1000 pi for the second signal. Now I wrote this little note here. How do we determine the highest frequency in the product of sinusoids? So here I'm going to get on a tangent just to explain when we multiply two sinusoids together, I'm assuming that x1 of t and x2 of t are sinusoids. It doesn't have to be sinusoids. Remember that, Fourier transforms allows us to work with aperiodic signals as well as periodic signals. But you can always break them down into sinusoids. Every single signal in all of existence can be broken down into sinusoids. So all the sinusoids will have frequencies associated with them. So anyways, whether the signal is periodic or non-periodic, how do we determine the highest frequency in the product of sinusoids? When I look at sine of something times sine of something, or sine of something times cosine of something, I'm not going to immediately be able to tell you what the highest frequency would be. I could maybe plot it in my graphing calculator and then, use the cool little graphing calculator functions to figure out the period of my resultant graph. But that takes a long time, and if you're trying to do it on a test, you're running out of time essentially. So anyways, how do we do this quickly? And so I'm going to get off onto a little tangent. Let's just say, for the sake of argument, just for illustration purposes, that x1 of t is sine of 500 pi t, and x2 of t is sine of 1,000 pi t. In the original problem, they didn't tell us what these signals were. They didn't tell us that these were sinusoids, or that they're sine of 500 pi or anything like that. It doesn't matter though. Just for the sake of argument, let's just say that they are. That would mean that y of t equals sine of 500 pi t times sine of 1,000 pi t. So what is the maximum frequency that is associated with this product? Well, let's use Euler's identity to see what happens, just to see what happens. So I'm going to take my sine of 500t and convert it into my Euler's identity for it. So I have j 500 pi t minus e minus j 500 pi t all over 2j, right? That's just straight from Euler's identity. And I do the same thing with sine of 1,000t, and I have that here. Now what we're going to do is we're just going to combine and simplify. That's all. So I took my my two 2j's, my two 1 over 2j's, and I combined them. So 1 over 2j times 1 over 2j becomes minus 1 over 4. So obviously the 2's multiply to 4, but you got to remember that j times j equals -1, right? So that's where this negative comes from. And you can plug that into your calculator. It'll still come out like that if you want to verify. And then I just combine these to become these. And then I combine them. Remember our exponent product rules? We can actually combine these to put all of these over a single e if we wanted to. And that's kind of what I want to do. But I want to do it in two terms so that I can use Euler's identity to reconvert back to a sinusoid. So that's what I did. So you can see that 1500, or wait, I skipped a step. I'm sorry, yeah, I messed this up. So what this came from is actually just the this times this. So we have the first term times the first term times the second term times the first term, and the second term times the second term. And that's where this came from. And so that's when I used the exponent product rule, and 500 plus 1,000 becomes 1,500. 500 plus 1,000 becomes, rather a minus 1,000 becomes a minus 1,500. And then a minus 500 times 1,000 becomes a minus 500. And a minus 500 times a minus 1,000 becomes a plus 500. And so I wrote these in order. So I have my 1,500s next to each other and my 500s next to each other. And then I grouped them so that I can use Euler's identity to reconvert them back to a sinusoid that I'm used to seeing. And so that's what I did here. And remember, I just have to rescale. I have a well-chosen one to rescale this, so I can keep this in the Euler's identity form. And I did the same thing with the second term. I want to rescale it using the well-chosen one so that I can keep this in the Euler's identity form. And then I convert them using Euler's identity. So I have a 1 over 2j sine of 1,500 pi t and a 1 over 2j sine of 500 pi t. And that's how you can easily determine the highest frequency in the product of sinusoids. So the highest frequency in the product of sinusoids, you're really just adding and subtracting. And if you've ever seen signal flow diagrams for like electrical engineering systems, like a radar system, for example, that's what I've seen in my career. You see sums and differences of signals all the time pop up everywhere, all over the schematic. And that's because of stuff like this, when you have the products of sines and cosines, or the products of trigonometric identities, rather. So we have our 1500 pi becomes our omega max, and our 500 pi becomes omega min. So back to our original problem, it asks us, we have a product of some signals, and they're both band limited to some, arbitrary amount. When you multiply two band limited signals, well, your highest frequency will just be the sum of those frequencies. And then, I'm sorry, I kind of forgot what this question was even asking us. I went on that tangent. This was asking us to, what is the Nyquist rate? Well, if we're going to determine a Nyquist rate, we need to know the maximum frequency. And that's why I went through all of that trouble to figure out what the maximum frequency was. Now that I know it, I literally can just plug it into the expression for the Nyquist rate. The omega, you're always going to double the omega. Well, if the omega max is 1500 pi, which we just determined, the Nyquist rate is going to be twice that. And so it's going to be 3000 pi. So that was a very easy problem if you knew what you're doing. I went on a big tangent, but hopefully that explains why you find your Nyquist rate to be 1000 pi. Now I have another little note before I move on to number 8, or before James takes on number 8. So just remember, product of sinusoids results in a power limited sum of sinusoids where each term is simply the sum of each frequency or difference of each frequency, or rather both. Kind of like with beats. So if you remember in the differential equations class, we looked at beats. So when you multiplied two signals that were very, very close to each other in frequency, so like if you had a 100 hertz signal multiplied by 102 hertz signal, you're going to produce a beat frequency of 2 hertz, right? Because that's the difference between those two. And so it's the same thing here. You're creating beats, but in that differential equations class, we talked about signals being very close to each other in frequency. They don't have to be close to each other. That is arbitrary. That is a subjective, arbitrary thing. Mathematically, it doesn't matter what the difference is. You're going to create beats. They're not going to be. They're not going to look like what we call beats. They're going to just look like an amplitude modulated signal. So, anyways, that's number 7, and hopefully that all makes sense. And now we're going to go on to problem 8, and James will explain that one for you guys.
All right, number 8. We're given this system here, and we're given the. So consider the following interconnected continuous time LTI system with the two subsystems in parallel with the impulse response of H1 of t and H2 of t respectively. If the unit step response so we were given the output y of t, or if the unit step response is y of t equals, that is worded horribly. Basically, this is the output if the input is y of t. And we also are given what H1 of t is. So we have this. The first thing we have to find is what is H2 of t. Then they want the overall H of t. So the overall impulse response to the whole system. If the system, then we have to determine if it's stable, why or why not. If it's causal, why or why not. Does the Fourier transform exist for H of t, and justify your answer? So, I just drew the picture and wrote down what we're given here. So for what is this? Oh, from the table, we're given that the Laplace transform of 1 over s plus, or 1 of e to the minus alpha t times the step function is this. And with our region of convergence, the real part of s has to be greater than negative alpha. So taking the Laplace transform, of y of t. Down here is kind of where we're going and why we're doing this. So the first thing I did was take the Laplace transform of y of t, and for y of t, it's -1/2 to the e to the -2t plus 1/2 e to the 2t. So that just transforms straight up to -1/2 times s 1 over s plus 2. With it's only valid if the real part of s is greater than -2, plus 1/2 of s minus 2, or 1/2 of 1 over s minus 2, and that's only valid if the real part is greater than -2, so that would be 2. So for the overall function, we're going to take our most limiting region of convergence, which in this case is +2. So the overall region of convergence of y of s is going to be greater than 2. The big thing with Laplace transforms versus Fourier transforms we know are going to converge. Laplaces have a real part and an imaginary part, so we don't know for sure. So that's why we have to put the condition that the region of convergence for when it will actually be true. So then doing some simplifications here, -1/2 times, that's just algebra. And all those simplifications bring us down to 2 over s minus 2 over s plus 2 with a region of convergence for the real part greater than 2. X of s is just a unit step function, so our transform is 1 over s, and the real part's got to be greater than 0. And h1 of s, again, was this e to the -2t, so that's another plug and chug conversion from the table. So the question originally asked us, what is h2 of s, I believe. Yeah, what is h2 or h2 of t? Sorry. So we know that y of s over x of s equals h of s, and we also know that because they're in parallel, h1 of s plus h2 of s equals h of s. So we just plug y over s times y of s divided by x of s minus h1 of s is our h2 of s. So doing that algebra, we get to h2 of s is equal to 1 over s minus 2 with a region. We still have the region of convergence of 2. So alpha is -2, which is also supported by this. Leave me alone. Sorry. So then our h of 2t is e to the 2t times the step function. So that is our time domain impulse response for this block right here. The next question is to the overall h of t. Now, there's two ways you can do this. The easy way, which is just add. We've found h2 of t, and we found, or you're given h1 of t, and you can just add those together, and that's your answer. Or if you want practice doing the reverse Laplacian transforms, we calculated the overall h of s up here. So you can do an inverse, just do some partial fraction expansion, and get your a's and your b's. So we split it up to this is 1 over s plus 2 and 1 over s minus 2. Doing the inverse Laplacian transforms. Hey, look, same answer. So it works. Part C asks us to, what does part C ask? Sorry. Is the overall system stable? Why or why not? So we test for stability by drawing. The easiest way is just to draw a region of convergence. We know that the real part of S has to be greater than 2. So this is your real and your imaginary plane. So everything's got to be greater than 2. Our imaginary axis is not included within the region of convergence. Therefore, it is not stable. And we're also asked if it's causal. And looking at it's in the right half of the plane and the right of the rightmost pole. So our poles were -2 and +2. So we are right of the rightmost pole. Therefore, we are also not causal. Or it is causal. The region of convergence of H of S is in the right half of the plane to the right of the rightmost pole. So it is causal. And that's our definition of causality. Or we have our poles, which I didn't put on this graph, but they are there at -2 and +2, and we're right of those, so it is causal. Last part, D asks us if there is a continuous time Fourier transform there. And no, it does not exist. The region of convergence, H of S, it's not stable. So therefore, you can't do a Fourier transform. You can only do the Laplacian and then restrict your domain to the region of convergence. So that's pretty much it on 8. This is I can guarantee you'll see something like this on the exam. Something where you use this y of s over x of s equals h of s, and basically do the differential equations that become algebra, and with your Laplacians, and then keep track of the regions of convergence. That's the big deal on those, is to keep track of the regions of convergence and do your transforms. So with that, I am going to give it back to Woody.
Sorry, I had to unmute myself. All right. Hey, did you do part D on that problem? I might have missed it. I was playing on my phone.
Yeah. It was basically the region of convergence doesn't include the imaginary axis.
Okay.
Is a statement. Basically, it's because you can't do a Fourier because there's no purely imaginary solution. Okay,
gotcha. Sorry, I stopped paying attention for a second, but I'm back now. So anyways, problem 9. Problem 9. That's what we're going to do now. We're going to do another Laplace transform. Remember, Laplace transforms are just like Fourier transforms, except for they include your real parts and imaginary parts, and not just imaginary parts like in Fourier transforms. So problem 9 asks us, consider a continuous time LTI system for which the input x of t and output y of t are related by the differential equation. And we're given the differential equation here. I'm not going to say it out loud because it's long. Part A wants us to determine the system function h of s, and then we want to sketch the pole zero plot for that. So let's go to my notes. Here I rewrote the differential equation, and it's a second order differential equation. Our coefficients for our differentials are 1, -2, -3, and 1. So if you need to put this differential equation into MATLAB, those are the coefficients those are the only values the only arguments you have to pass to the function, if I were to say that correctly. Those are basically the parts that matter. It's the 1, -2, -3, and 1. So part A asks us to take the Laplacian transform of that. And so we use this Laplace transform pair where we have the derivative of x of t becomes the transform pair x of s times another s. And if we take multiple derivatives, we're just adding on s's. That's all we're doing. So the second derivative of x of t will become s squared x of s. So anyways, I go ahead and plug and chug that. So we have s squared because of the second derivative here, y of s. And then we have -2 through the linearity property. The -2 is unchanged. And then we have one derivative, so we have 1s. And then we multiply that by the arbitrary transform of y of t. And then we have a -3 through linearity is still there. And we have no derivative, so we're just going to take the transform of y of t, and that becomes y of s. And remember, we're talking in terms of, we're not explicitly given what y of t is. It doesn't matter. So we're going to be working in terms of implicit terms. And then we're going to take the Laplace transform of x of t, and that becomes x of s. Remember, s equals sigma plus j omega. So it's a complex number. Just wanted to say that for GWiz so that we remind ourselves what it is. So now I'm going to take the y of s term out of all of these, and that's what I've done here. So I have a single y of s terms times the quantity s squared minus 2s minus 3, and then all equals x of s. So what that was useful for is we know by definition that a transfer function, h of s is a transfer function, equals, and the transfer function always equals this, that transfer function always equals the output over the input. We can call these z's and a's and whatever letters we like. By convention, we use y for output and x for input, but whatever it is, your transfer function is always your output over your input in the frequency domain. So if I have an expression like this, well, I want to put my x over here and get rid of this weird, I guess I might call it a coefficient in this case. So I'm going to divide both ends by s squared minus 2s minus 3. So that turns into this. So if I take x and put it over here, it looks like this. And if I take, when the x is gone, it becomes 1. We have 1, an implicit 1 here. It becomes 1 over s squared minus 2s minus 3 here. So that's the expression for h of s. And that's what the problem asks us for that, right? Determine the h of s. Now that we have h of s, plot it. We want to sketch them. So I have one more step here. This could be a final answer if we weren't asked for anything else. But if I'm going to determine zeros and poles, I need to split this up into these things. I forgot the algebraic term for this, but you got to decompose this into this. So this becomes s minus 3 times s plus 1. Now we can easily determine our zeros and poles. Well, there are no zeros because we don't have any variables up here. There's no s term to be equal to 0, so we have no zeros. There's no zeros here. So on my plot, I don't put any zeros. Remember, the symbol on a plot for a 0 is just a circle, so we don't have any circles up here. Now there are 2 poles, though. And a pole is basically just where does the denominator equal 0? And whenever denominators equal 0, that is an illegal operation because it will result in infinity. 1 divided by 0 equals infinity. So anyways, where does this equal 0? Well, it equals 0 at s equals 3 and s equals negative 1. So those are my 2 poles. So when we plot poles on a graph, we use x's. I don't know if you can kind of tell, but, well, actually I didn't do number 8, but on number 8, I just put little dots, and then I realized, oh crap, I need to use x's, not dots. That way I don't confuse it with zeros. So make sure you mind that when you're plotting stuff like this, zeros and poles on graphs. So anyways, I have my 2 poles at 3 and negative 1. And so I just put my little dots here to indicate that the entire range, the entire range at that single point is a pole. In other words, it doesn't matter what value of j omega could be. If our sigma is 3, it's a illegal value. So that's part A. Now part B asked us determine h of t if the system is causal. Well, part C and part D are going to ask us the same exact thing. What is h of t under different conditions? But the first condition we're given is causal. And you have to remember, under different conditions of causality and stability, h of t will be different. Because in the Laplace, the Laplace is more complicated than a Fourier. You can have different Laplace transforms based on your conditions of the system. And you can see that on the table. And I'll get to that in a second. So let me scroll down to B. So if causal, if a signal or a system is causal, that means by definition that the region of convergence is the right half plane of the rightmost pole. So in part A, I drew h of s, but I didn't shade anything. So this does not tell me, this is only half the picture of what our system is, or signal. We have to define our region of convergence for it to become a description of a system, of a full system. So in part B, we're given that condition. We want it to be causal. So then I took my same image from part A and I shaded the rightmost pole to the right half plane of the rightmost pole. And that tells us that this system is causal. The next thing I have to do is I have to take my h of s, and I need to use partial fraction decomposition to split it up into individual terms that then can be transformed back into the time domain. So this right here, I can't transform that back into the time domain because I don't have an entry that looks like this in my table. Now, after I solve this problem, I could record an entry. So anytime a transfer function looks like this, it becomes this in the time domain. I could do that if I wanted to. And in the engineering world, we do that. Every single time you have to calculate a new transform pair, just record it. You know, you save money next time you have to do that same transform pair. So in MATLAB and other industry tools, you have libraries full of Laplace transforms. But in our table that we're given for the exams, we have a very limited short list. So anyways, we have to do a little legwork to turn this into a form that I can then transform using my table. Otherwise, I could do this explicitly using the definition, but that sounds like a nightmare. So screw that. Let's use partial fraction decomposition because it's way easier. So the mechanics of partial fraction decomposition start here. Like this is me doing partial fraction decomposition. So I restated what h of s was. And then my first step in partial fraction decomposition is I want to split these terms up. I want to split this from this. And that's what I did here. S minus 3 and S over 1. I need to determine this A and B such that this whole quantity becomes this. In other words, that's what I'm doing. So now that I've written these A and B terms here, I need to figure them out. So the first thing I do is, I forgot the words they use in algebra, but I need to take this term and multiply it by this A, and I need to take this term and multiply it by this B. So that's what I've done here. In other words, these are well-chosen ones. So S plus 1 over S plus 1, that is 1. Ones are implicit. And any time I express a term or a value of anything, there's always a 1 next to it because anything times 1 is that same thing itself. So anyways, I just arbitrarily chose this well-chosen one and this well-chosen one. Crap. This one right here. That way I can combine these into a single term, which I've done here. I mean, I did distribute this A to these two terms and this B to these two terms first. I didn't write that explicitly, but we know that A times S, there's AS, and then A plus 1, so there's A times 1. There's A times 1, and then B times S, and B times -3, and I have my BS and my B times -3 right there. And all of this is over a single term now, and that's useful and nice and neat. So the next thing I do is I group like terms. Of these 4 terms, I have 2 that are like each other, and then 2 that are like the other 2. So I have an AS and a BS, so those are kind of like each other. And then I have a A and a -3B, those are like each other too. So I group them together. So I have A plus B times S, and then I have A minus 3B. What that's useful for is it allows us to then set up a series of equations, a group of equations that I can then solve to determine A and B. And I did this using linear algebra. Hopefully, I don't know if linear algebra is a requirement for this class, but I hope most of the people that are watching now have taken linear algebra. You can do this by hand. It just sucks, but you can. But in linear algebra, I have 2 equations and 2 unknowns. I just rewrote that here. My first equation is this. A plus B times S. Well, you got to remember that this whole thing must equal what we originally started with. So these are the same. So we can ignore those. But this whole thing here equals 1. And that's how you determine your 2 equations. So let's see. So I have A plus B equals 0. This is A plus B equals 0 because I have no S term here. There's no S term to be seen. Therefore, this whole quantity, if this entire thing is equal to 1, this whole quantity must equal 0. Therefore, A plus B equals 0. And then same thing here. If this whole quantity equals 1, and we've already determined that the first half equals 0, well, then that means that the rest of it must equal 1. And that's our second equation. So a minus 3b equals 1. So we just determined 2 equations and 2 unknowns. Now we can use linear algebra to put this into a matrix form. And that's what this is my preferred method. Other people would probably just solve this explicitly by saying, well, a equals minus b, and then you plug in minus b into this a term here, and then this is an easy example because we only have 2 equations with 2 unknowns. If we had 5 equations with 5 unknowns, you would not want to do that by hand. You would want to use linear algebra and put it in matrix form, but I'm just used to using matrices, or matrices. So I did that. So I have a 1 coefficient, a 1 coefficient, and a 0, and I have a 1 coefficient, a minus 3 coefficient, and a 1. So here's the matrix representation of that. And then I plugged this into my graphing calculator, and I took the RREF, the reduced row echelon form of that, to determine my A and B. And if you don't know what I'm talking about here, then please review your linear algebra. If you haven't taken linear algebra, then I guess I'm going a little over your head, but hopefully everybody has. And when I plug this into my calculator, this is the result. A equals 0.25 and B equals negative 0.25. And turning them back into fractions, that equals a quarter and a negative quarter. So now that we've determined our coefficients, we're just going to plug them into our expression that we wanted from the beginning. And the reason why we wanted this from the beginning was so that we could take the Laplacians of each term individually. Remember, through the property of linearity, these are individual Laplace transforms. And I have entries on my table that look like this, so it makes it easy. So I plugged my newfound coefficients into that expression, and now I can take the Laplace transform. But wait, what is the region of convergence? Before we can take the Laplace transform, we must define the region of convergence. But luckily we did that already. We did that here. So the problem told us it was causal, therefore our region of convergence was the right half plane of the rightmost pole, so we then shaded in the right half plane of the rightmost pole. Remember, our 2 poles are at -1 and 3. Now we can determine our region of convergence. So if I'm sorry, Laplace transforms, because we know our region of convergence. So here I just rewrote our region of convergence. And remember, our region of convergence does include both terms, the 3 and the -1. These are our 2 poles. When it's causal, we only care about the rightmost one, which happens to be 3. But you still need to know them both, because this expression cannot be evaluated at -1 because it would equal infinity. It'd be divided by 0. So anyways, knowing all that, we're just going to go over to our Laplace transform table. See which one of these would be that. I think it's this one. Laplace transform. I'm going to scroll down until I find the table and find that entry. So this looks like, these 2 things look like an expression that we have. So our expression is 1/4 over s plus, I already forgot it, s plus s minus 3 and s plus 1. Oops. But which one of these do we use? So these 2 look the same. How do we determine it? Well, it's based on our region of convergence. Since we have a causal system and we are using the rightmost pole, our rightmost pole is we're going to the right of the rightmost pole. That means the real part of S is larger than to the right of our rightmost pole. Our rightmost pole is 3. So that means we're going to use this top one and not the bottom one. So that means our transform pair becomes this exponential times a unit step. And we're going to be plugging in our A for A. That's actually an alpha, but I'm going to call it an A. And then that's it, really. It's just very straightforward. So doing that, here's my coefficient that we determined. This is A. Here's the transform pair. We plugged in A. This is A, or alpha, rather. And there's our alpha. And then same thing with the second one. We have our coefficient. Here's our coefficient. Our transform pair becomes exponential times a unit step. And we plug in A, or alpha, is a -1 this time, because we have a plus here. So you have to go with the opposite of that. So we have a -1 here. So that's your transform pair for part B. Now part C, we're going to do the exact same thing, except for we don't care about causality anymore. We care about stability. So what do we do here? Well, the definition of stability is that you include the j omega axis on the S plane. Remember, the S-plane is a real part axis and an imaginary axis. We call the real part sigma. We call the imaginary part j omega. Now, if it's stable, that means we include in our shaded region of convergence, we include the j omega axis. And that's by definition. So our region of convergence will look different when we write it in mathematical terms rather than just visualizing it graphically. So if we compared these, so compare this to, well, I didn't write it explicitly here, I just drew it. But yeah, our regions, oh yeah, I did write it. I wrote it right here. So you need to compare this to this. They look different, don't they? And what that translates into is that we're going to use a different transform pair on our transform pair table than we did in part B. And that's the only difference. So going back to this thing here, this time our region of convergence follows this pattern. Therefore, we must use this transform pair. Now, mind you, we have two terms here. We have two terms that we have to worry about. So we're actually, one of our terms still meets this condition, but the other term does not. It meets this condition. So therefore, one term in the time domain will become this. The other term will become this. So let's show that. So this is h of s given to us again, and our region of convergence makes it so that our first term, remember our first term is going to be the real part of s is lower than or less than 3. And then our real part of s for the other term is greater than -1. And you can see that graphically there. So our transform pairs become this. So remember on our table, we have these two terms. So my first term is going to have this negative here and this negative in the unit step. And then the second term will just be regular positive here and a regular unit step. And you see that here. You have a negative here and a negative in the unit step. And then you have a regular exponential and a regular unit step. And you might wonder where this negative came from. And that just came from our b coefficient being a negative value. All right, so that's part C. So part D, what do we do in part D? Well, part D is the same thing, same transfer function, the same system, but this time it's going to be neither causal nor stable. And what that means is that we cannot be to the right half plane of the rightmost pole, and we can't include the j omega axis. So how do we do that? The only way we can do those two things is by shading the left half of the leftmost pole. And that would become a system that's not causal nor stable. And writing that mathematically, we say that the real part of s is less than 3. It's not shaded here. But it's also less than -1. So that's why we can't shade in this region, because it's also less than -1. So that means that on our transform table, both of our terms are going to be real part of s less than our number, our pole. Therefore, both terms will have this weird negative in front of the exponential and this weird negative inside this unit step. And we see that here. We have this negative here and a negative here. And then we have a negative in this unit step, and we have a negative here. But since b was a negative value already, we have a double negative, so it becomes positive. And that's part D. Now, that's it for problem 9. And we've solved everything, but I just wanted to add, you know, sometimes we get bogged down in the mechanics of solving these problems, and it's almost like you have blinders on and stuff. But some people might ask, well, how come we mess around with systems that are not causal and not stable? If you can't create them in real life, why even worry about them? Why are we practicing these skills for systems that are impossible? The answer to that question is yes, it would be impossible to create a system that does this stuff in real time, like an analog system that does this in real time. But you got to remember, we have computers and we have discrete systems. A computer can record something, and then you can manipulate it at any point in time after that. So if I have a recording from a recording studio of somebody singing, and then a year later I give it to an engineer and I tell them, hey, manipulate this recording in some way. Since it's a recording, you don't have this limitation of past versus future. and all that kind of stuff. So you don't have to worry about causality anymore because the whole thing's recorded. You can define your zero time axis anywhere in that signal, anywhere in that recording. And so you can still mess with systems that might look like this. Same with stability. You can still make unstable systems. It might, and in fact, I think some systems are made purposely unstable. But anyways, I'm not going to take up too much more time, so we're going to give it back to James, and he's going to start with problem 10.
Hi, how's it going? All right, we're doing number 10. Number 10. So now we're doing Z transforms because we have discrete time signals, which is basically the Laplace transforms of discrete time signals. So consider the following one of our favorite types of systems with one impulse response feeding another impulse. And we're given both of our impulse responses, and we're asked to find the Z transform of both H1 and H2 and specify their regions of convergence, or then asked to calculate the total impulse response and sketch its pole zero plot and its region of convergence, and then determine if there's a discrete time Fourier transform. Could we do a Fourier transform for this instead of a Z transform, and justify our answers? This one's pretty straightforward. So we have this signal, delta n minus 1 minus delta n minus 2, and the signal h, or 1/2 the n minus 1 times u of n plus 2. So for 1, it's a time shift. Basically a time shifted delta function. So we use the property of a time shift from our tables, which I believe is 10 something in this one. Should look this up before. Yeah, property 1052 from table 10.1. So we basically the deltas all go to 1, and then we're left with the Z with the coefficient of the time shift. And so our H1 is Z to the -1 and Z to the -2. And from our common transforms pairs, our region of convergence for the delta function is actually, if we looked at 10.2, number 4, that's our signal, which is the time shifted delta function, but it's all done at once and in a nice neat format. And also that specifies our region of convergence, so it's all Z except for 0. So our region of convergence for number 1 is Z not equal to 0. For number 2, our H2n, 1/2 the n minus 1 times the unit step function of u of n plus 2. So we want our n's to match so that we can use time shift. Way back before I did this manually, but instead this time I'm going to actually use the time shift. So we find out that we basically need to figure out how we can make this n minus 1 have an n plus 2. So we subtract I put an n. I use n naught. Use whatever variable you want, but n minus n naught. This is our time shift. Minus 1 equals n plus 2. Solving that, you have your n naught equal to 3. So that's your time shift, and you can pull so you basically pull out the 1/2 to the -3, and then you have 1/2 times n plus 2 times u of n plus 2. This equation is equivalent to this equation. So you perform your Z transform, and this is just a number. So 1 over 2 to the 1 over 2 to the -3rd is 9 or 8, and Z and this transform, the transform of n plus 2 becomes Z squared I didn't list the transform, but you, where is it at? Well, it's just your time shifted. Your time shifted for that transform, which is transform 5. So it's so it's number 6, which is your time shifted transform. So then that's we'll go with just the time shifted, 5 time shifted. So you take it times z squared because you're time shifting by 2, and putting all the coefficients together, you get 8 times z squared over 1 minus 1 over 1/2. That's a 1/2. It's horribly written. Z minus 1. And a region of convergence, the magnitude of z is greater than 1/2, but less than infinity. So that specifies our z transforms. That's part A. Part B asks us to determine the overall system transform, or compute the h of z transform of the overall system and sketch the region of convergence. So we're convoluting in the time domain, so we're just multiplying in the frequency domain. So our overall is this is h1, or this is h1, this is h2. Some algebra gets you to the answer in the key. Nice little simplified answer. So here I'm just distributing the 8 to address the numerator, and then multiplying by z over z, which is our 1, to get your denominator, numerator, and basically get rid of the z's and the minus, so to get everything rationalized. Our pole 0 plot, our most conservative region of convergence, was h2, which is 1/2. So because we have that region of convergence for that one, that's the driving region of convergence for the overall function. So graphing that as a circle with a radius of 1/2, and everything outside that circle is in a region of convergence, and everything inside that circle is not. The next part C asks us: is there's a discrete time Fourier transfer exists for this? Total impulse response? And the answer is yes. Much like in Laplace transforms, where the JW or the S or whatever the imaginary axis has to be included. For Z transforms, that's the unit circle. So the circle of radius 1. And because the circle of radius 1 is within the our region of convergence, we can do a discrete time Fourier transform. I didn't sketch the poles or zeros on here, and that's my bad. So our poles would be, looks like 0 and 1/2, or our pole would be 1/2, and our zeros would be 0, just 0.
There's a couple more too. You have a 0 at 1.
Oh yeah.
A 0 and a 0 at 1, and then you have a 0 at 1/2 and a 0 at infinity. You can't forget about those infinities.
Oh yeah, good point. Thanks. Yeah. So the way we got those, just looking at the equation, looking at the overall equation, and seeing when either the denominator is 0 or the numerator is 0. So if the numerator is 0, then it's a 0. If the denominator is 0, then it's undefined and it's an infinite, and it's a pole. So I don't know if we covered that, but that's how we got those. But yeah, you'd have to, so you have 0, 1, and 1/2, and infinity. Cool. All right, moving on to the last one. Giving it back to Woody here.
Okay, back to me. I want to add one more note about these finding the zeros and poles. For part B, I am presenting, right? I hope I am. So when you got your final result or your almost final result as h of z equals 8 times the quantity z minus 1 over quantity 1 minus half z to the minus 1. When James talked about getting that rationalized and putting it and multiplying by z over z, which is a well-chosen one, there is a practical reason for that. It's not just to make it look pretty, but it literally allows you to see more zeros and poles than you otherwise would be able to. If I looked at just this expression here, it looks like I only have one pole at positive, or I'm sorry, positive half, and I have 1 0 at 1. But that's not all of your poles and zeros. You have more than that, but you won't be able to see them until you rationalize this. You rationalize it by finding a well-chosen one and then distributing those z's accordingly. Then you get this final form like this. And now we have this new term here. We have this extra z here, and that tells me that I have another 0 at 0. So when z equals 0, I have a 0. When z equals 1, I have a 0. And then down here, when z equals a half, I have a pole. Now, how did I determine this infinity being a pole? Well, you plug in infinity to z in the numerator, and that, well, we don't like infinite results because infinity is undefined. By definition, it's undefined. As funny as that sounds. But yeah, you have to remember that. So anyways, that's just one additional little note to that. Not to step on your toes or anything like that, James. But all right, so let's get on to problem 11.
You're helping that out.
No problem. Number 11 is the last problem on this course, or not this course, but this review. And number 11 is another z transform, and this time it says the transfer function of a discrete time LTI system is given by this expression. So we're given a transfer function. It asked us then what is the difference equation that describes that. So on previous problems, it gave us the difference equation, or like in the continuous time problem, it gave us a differential equation, and then we had to come up with the transfer function. This time we got to go backwards. So let's go ahead and do part A, and then we'll move on to part C, the B, C, and D later. So part A, what is the difference equation? If this is our transfer function, and here I just rewrote it from our problem, how do we determine a difference equation? Remember, a difference equation is just the same thing as a differential equation in continuous time. All right, so transfer functions by definition are our output divided by our input, and we use the variables y for output and z for or x for input. But if we're given this is our h of z. This is equal to y of z over x of z, and here I distributed these two quantities multiplied by each other. So then I have a single string of terms, I guess. What did I do? Oh, so here I rewrote it again in simple terms, and a difference equation is defined as I think you're presenting now, James. Sorry, your screen just popped up in my field of view.
No, I have you as the presenter.
Oh.
I just turned on my now I'm presenting. Wait, back here.
All right, so sorry. So back to this. If we want to put this in a form for a difference equation, we have to take this and bring it up here, and we want to take our x of z and bring it over here by itself too. And so I've done that here. So this is essentially our difference equation right here. But we're used to seeing difference equations in the time domain. So we gotta go through another couple steps to do the z transform on it, the inverse transform rather in this case. So the inverse transform, and I forgot my little -1 here, but in notation the inverse z transform should have a little -1 here. But anyways, the inverse z transform of all this stuff makes it a little easier if I distribute this y of z to each of these three terms. So I did that here. So y of z times 1. Here's y of z times quarter z to the -1, and then here's y of z times 1/8 z to the -2. Now that I've done that, using the linearity property, these are individual z transforms. I have four z transforms. So I have 3 on the left side of the equal sign, and then I have 1 on the right side of the equal sign. So 4 terms. And you just go to the transform table. We know that the inverse of y of z will become y of n, So that one's easy. This one, same thing, except that I have a coefficient. Using linear property, that coefficient is undisturbed. But this z to the minus 1 becomes a time shift, looking at the time shift property. So we have a y of n to the minus 1. And then same thing with this third term here. We have some coefficient, minus 1/8. And then we have a z to the minus 2. That just means that we have a time shift at a value of 2. So it becomes y to the n minus 2, a time shift of minus 2. And then same thing here. The inverse transform of x of z is x of n. So that was pretty straightforward. So let's see what we got to do on part B. Part B wants us to find the impulse response h of t if it is a two-sided signal. Is the system causal y and is the system stable y? So just like in the last problem that I worked, I think it was problem 9, we're doing the exact same thing. We're going to be finding h of t's under different conditions. At first, we're going to do it for a two-sided, then we're going to do it for a right-sided signal, then we're going to do it for a left-sided signal. So the only thing that's going to be different is our h of z's will be the same. What differs is our regions of convergence. We have 3 different regions of convergences here. So just like on problem 9, we're just going to be using different transform pairs based on those regions of convergence. So part B, I have a lot of scribble here. It looks like it's a little bit more complicated than what I just said, but only because we have to determine h of z in a way that allows us to make easy transform pairs. So the way h of z was given to us, there is no transform pair table. There's no transform pair entry on the table for this. Now, once we've gotten through the legwork and created this, then we could add it to the table if we wanted to. We won't need to for our exam or anything like that, but so I went through all the trouble to do that using partial fraction decomposition. You saw how I did that in problem 9. It's the exact same methodology. I have 2 terms that I want to split into a sum of those things. So there must be some value that I can place over each of these 2 terms so that the sum of both full terms equals this expression. And here I'm going through the mechanics of that. It's the exact same thing we did before. I put everything over a single denominator. Then what is it? I lumped like terms. So there's one lump there, and here's a second lump here. Notice that all of this has to be equal to our original expression, equal to 1. So a plus b must equal 1, and minus quarter a plus half b all times z to the minus 1 must equal 1. But notice there's no z term here. Therefore, this stuff must be equal to 0. And then a plus b equals 1. So here I have 2 equations with 2 unknowns. Again, I've already defined my 2 equations. I put it into matrix form. The matrix form is just our coefficients of each of these terms. So I have 1 here, a 1 here, and a 1 here. And then that becomes that top row. And then I have a minus quarter here, a plus half here, and a 0 here. And that becomes our bottom here. And then I put that into my graphing calculator, and I took the RREF, reduced row echelon form, and that gave me my A and B terms. So my A and B terms were 2/3 and 1/3. And mind you, you could have done this by hand if you wanted to. Since it's only 2 equations, it doesn't take too much time to do that. And you certainly could do that on the exam without losing too much time. But when you have a lot more complicated, when you have more terms, and then you end up having like a lot more equations with more unknowns, the matrix form is a lot easier. Anyways, now that I know my 2 coefficients, I can split them. These are now in a form that I can pair them with a transform pair from my tables. The only thing I have to remember is my region of convergence. How did I determine my region of convergence in this case? Well, it was partially given to me. I say partially because the problem told me that this signal or system was two-sided. And what that means, by definition, two-sided means that my Z must be the shaded region must be a ring between my 2 poles. And if you don't believe me, let's go to this. See what two-sided means. A two-sided signal means that we have a ring bounded by poles. The shaded region is a ring bounded by 2 poles. And so that's what I drew here. I drew a ring shaded bounded by 2 poles in the z-plane. Remembering that, I'm going to look at my z-transform table. Scrolling down. And which of these is in a form that I recognize? Well, these two are. So now the only difference between these two is the regions of convergence. And remember, I have two terms. In both terms, one of the terms, my z is greater than the pole, and my other term, the z is less than the pole, because it's, you know, it's a ring, a shaded region bounded by the two poles. So one of my terms will end up being this exponential to the n power times the unit step, and my other one will become a negative of that exponential times a negative unit step time shifted. So just remember this and this. So one of them will be this, one of them will be this, and let's see what I wrote. It looks like I did exactly that. I have, one of them has a negative, and it has this weird negative and time shift in the unit step. And then the other one's a positive and has a normal time step. Now you might wonder where this negative came from, and that came from, where is it? That came from this. That was, why do I have a negative there? So negative and positives don't mean anything when you're in a polar form, because this pole at positive half is also equal to the same pole at negative half. Same with the positive quarter and a negative quarter. So I'm a little embarrassed. I should have already known where this negative came from. What problem was it? We have a oh, here it is. This expression here. So our pole, when we calculated it algebraically, it had to be a negative half, because a positive half, well, 1 plus positive half times positive half does not equal 0. So it has to be a negative half, and that's where that negative came from. So when you look for stuff like this and you're writing it down, remember that you can't just look at things graphically. You have to look at the algebraic form of it, or the mathematical, form of it. And remember these types of things, that you can get the final answers in the correct form. So that's where that came from. So that's part B. Part C is going to be the exact same thing, except for we have a right-sided signal. And by definition, a right-sided signal means that we have the outside of the circle of the outmost pole. So when I drew my region of convergence, I had to shade everywhere outside of the outside pole. My outside pole is a half. My inside pole is a quarter. So I shaded everything outside of that. And this is also the definition of a causal system. A causal system is the shading outside the rightmost pole, or the outside pole. So there's no difference except that the region of convergence is different. So this time, our region of convergence is going to be, both terms will have a region of convergence that is greater than a half. So when I go to my transform pair table, I'm going to be using only that one term that was z greater than my pole. I'm not going to have any terms that have this weird negative and this weird time shift in the unit step. Both terms will look like this. So that's exactly what I wrote. I have a positive and I have a normal unit step, and I have a positive and a normal unit step. Now the question did ask, is it causal and is it stable? Well, the definition for causality is that in the z plane, in the z transform z plane, which is in a polar coordinate system, we have the shaded region of convergence is the exterior circle of the outside outermost pole, which is exactly what I've drawn here. Now stability, the definition of stability is that it includes the unit circle. Well, the unit circle is the circle of radius 1. I drew two circles here. I did not draw the unit circle, but this my first circle has a radius of a quarter. My second circle has a radius of a half. Well, if I drew a third circle, it would have a radius of 1. Let's see, a 1 would be out here. If I drew this circle with radius 1, well, that's included in the shaded region. So therefore, this system is stable. Now, part D, we flip all that on its head, and we say, well, this time we want h of n to be left-sided. Left-sided means that our region to convergence, I didn't draw it here, but our region to convergence will be the inside circle here, on the inside of the innermost pole. And if I wrote that mathematically, that's what it looks like here. So only difference is our region of convergence has changed. This time, when I'm looking at the transform pairs on the table, both of my terms will follow this convention here. Both terms will be less than a quarter. Therefore, both my terms will have to have this weird, ugly minus sign and this time shift and time reversal. So you can see that here. I have this weird, ugly minus sign here and a weird, ugly time shift and time reversal. And then I have my minus here and my unit step time shift and time reversal here. Remember that your poles, you have to keep your algebraic poles, not your graphical poles, so that 1/2 still remains negative here, and I still have a positive quarter here. But other than that, that's the expression for the transfer function in the time domain. But we still have to determine, is the system causal and is it stable? Well, the definition of causality is that it includes the unit circle, the unit circle. If we shade the inside of this circle, and my circle of radius 1 is all the way out here, well, none of that shade is going to be on the unit circle. So it does not include that unit circle axis, and therefore it's not causal. Stability is, oh, I said that backwards. I'm sorry. Stability is, it must include the unit circle, and so if we shade this inner circle, it does not include that unit circle, so it's not stable. Now, causality, the definition of causality is that it is the outside of the outside pole, but we've shaded the inside of the inside pole. Therefore, this system is not causal, and that is it. That is it for number 11. So we have finally completed this this final exam practice review, and if you guys have any questions, let us know on Piazza tonight or tomorrow, and tomorrow we're going to make another video answering anybody's follow-on questions. With that, I guess I don't have anything else to say.
All right, guys. Just want to wish you luck on the test coming up. I took a look at it. It doesn't look that bad. And yeah, just be careful with the negatives. Be careful with your regions of convergence. Keeping track of those, and you really should be fine. Anyway, any questions? Get us on Piazza. Until then, take care. We'll end the broadcast.